Imagine a star so dense that a single teaspoon of its matter weighs more than a mountain. Deep inside a neutron star's core, physics behaves in ways we can barely comprehend. What strange forces are at work in this extreme frontier of the universe? In this video, we'll explore the mystery. If you enjoy it, please like, subscribe and share, and tell us in the comments which part of neutron stars fascinates you most. Thank you for watching. Now, let's begin. The surface and outer crust of a neutron star form the first barrier between its unseen interior and the surrounding space. At the very top lies a thin atmosphere only a few centimeters deep, made of light elements such as hydrogen and helium, if the star has recently accreted matter or heavier nuclei, if its surface has been altered by earlier nuclear burning. This layer is tenuous in thickness, but decisive in effect since it shapes the spectrum of radiation escaping into space. Observations in X-rays depend on how this atmosphere absorbs, scatters and reprocesses the heat from below. Even though it is nearly weightless compared to the bulk of the star, the atmosphere is the visible face of the object. Beneath this outer film begins the crust proper. In the outer crust, pressure rises to unimaginable values. At these densities, the familiar architecture of atoms cannot survive. Electrons are stripped from nuclei and forced into a collective state called a degenerate electron gas. This gas is not like air or vapor on Earth. It is instead a quantum sea where electrons fill every available energy state up to a sharp limit called the Fermi energy. No two electrons may occupy the same state, so increasing density does not crowd them into closer positions, but instead drives them into higher momentum states. The consequence is that pressure comes not from temperature or motion in the ordinary sense, but from the quantum requirement that particles remain distinct. This degeneracy pressure, which does not weaken as the star cools, helps hold up the crust against further collapse. The nuclei that remain in the lattice are unusual. Under conditions far less extreme, iron nuclei dominate stellar interiors, because iron is the most tightly bound configuration at ordinary densities. Inside the crust, however, electrons are squeezed so tightly against protons that new neutrons are created through inverse beta decay. The nuclei thus become neutron-rich, filled with more neutrons than any stable isotope observed on Earth. These exotic nuclei assemble into a crystalline lattice. Unlike the lattices in terrestrial metals, which are flexible and subject to vibrations, the lattice in a neutron star is locked into place by forces of immense strength. Its thickness extends for hundreds of meters, and the mass contained in this layer exceeds that of an Earth-sized planet. The lattice supports both the rotational stresses and the anchoring of the magnetic field lines that thread the star. It is rigid enough to fracture, and such fractures may explain sudden starquakes observed in magnetaires where energy is violently released into space. The heat of a newly born neutron star initially reaches billions of degrees, yet the binding energies within the crust are so great that this heat cannot melt the structure. The reason is that thermal agitation is insignificant compared with the pressure and electrostatic attraction between nuclei at these densities. Thus the crust solidifies almost immediately after formation and remains in a crystalline state despite gradual cooling. Electrons in the outer crust move at relativistic speeds because their Fermi energy is extremely high. This grants them both high conductivity and high pressure. They carry currents that shape the magnetic configuration and allow heat to be conducted efficiently through the crust. In this way, the outer crust acts as a mediator between the deep thermal reservoir inside and the radiation observed at the surface. When astronomers analyze X-ray light curves and spectra, they are indirectly probing how heat flows through this crustal layer. If the star is part of a binary system and draws gas from a companion, matter accumulates on the surface and eventually sinks into the crust. As it is buried deeper by later deposits, the pressure ignites nuclear reactions. Hydrogen may fuse into helium, helium into carbon, and heavier chains may follow. These reactions proceed in flashes that produce X-ray bursts. The byproducts of these bursts, sometimes called nuclear ashes, contain heavy isotopes that gradually become part of the crust. Over thousands of cycles, the composition of the outer crust shifts with consequences for conductivity and heat capacity. Thus, the crust is a site not only of static structure but of dynamic change driven by accretion and nuclear burning. The density in this region ranges from about 10 to the 11 grams per cubic centimetre, near the top to nearly 10 to the 14 grams per cubic centimetre at the base. These values defy intuition. A teaspoon of material from the outer crust would weigh as much as a mountain. The mass contained in the crust, although small compared with the star as a whole, is vast in human terms. This makes the crust an arena where both nuclear and astrophysical processes intersect. The electrical conductivity of the outer crust is another critical property. Because electrons are highly mobile, magnetic fields are essentially frozen into the material over astrophysical timescales. This means that the field lines anchored in the crust evolve only slowly unless disturbed by fractures or currents. In highly magnetized neutron stars called magnetars, stresses from the field can exceed the strength of the lattice, leading to sudden ruptures. These ruptures may produce bursts of gamma rays and X-rays observable across great distances. Thus, the solid but fragile nature of the crust is tied to phenomena that reach astronomers' instruments on Earth. The bottom of the outer crust prepares the way for the next stage of matter organization, the neutron drip point. Here the density becomes so high that nuclei can no longer hold on to their excess neutrons. The neutrons begin to drip out, forming a sea that surrounds the nuclei. Although this transition belongs to the inner crust, the conditions for it are set by the gradual enrichment of neutrons in nuclei across the outer crust. As more and more neutrons are created by electron capture, stability is stretched to its limit until the nuclei cannot contain them. Laboratory studies of neutron-rich isotopes help physicists estimate where this threshold occurs. Experiments with heavy ion beams allow researchers to create nuclei close to those expected in the crust, though at much lower densities. By comparing their properties with theoretical models, scientists refine the equations of state that describe the crust. Theories of neutron star cooling also depend heavily on how heat is stored and conducted through this region. Observations of cooling curves from young neutron stars show how surface temperature decreases with time. Matching these curves requires careful modeling of crustal physics, including electron transport, lattice structure, and nuclear reactions in accreted matter. Each observation provides an indirect test of the crust models, making the outer crust one of the most constrained parts of neutron star interiors. The outer crust then is not only the gateway into the deeper regions of the star, but also the region that connects directly with telescopes. It is the arena where quantum mechanics, nuclear processes, and astrophysical observations overlap most strongly. Its rigid lattice, its relativistic electrons, and its neutron-rich nuclei are the starting points for the stranger forms of matter found deeper inside. The transition from the outer crust to the inner crust of a neutron star is marked by the onset of neutron drip, a process that fundamentally changes the nature of matter. In the outer crust, nuclei have become progressively more neutron-rich, as pressure forces electrons into protons producing neutrons. Yet these neutrons remain bound within nuclei until the density reaches a critical threshold. At that point, nuclei can no longer hold on to all their neutrons. Excess neutrons begin to leak out, and a sea of free neutrons forms around the nuclear lattice. This threshold density is called the neutron drip point, and it occurs at values near 4 times 10 to the 11 grams per cubic centimetre. The change is profound because matter now consists of 2 interpenetrating components a lattice of neutron-rich nuclei, and a background of free neutrons. These neutrons are not bound to individual nuclei and move more freely than the lattice ions. The inner crust thus begins as a mixture with nuclei forming a crystalline scaffold, while neutrons drift among them. The degenerate electron gas remains present, continuing to balance charge and provide pressure support. This three-component system of nuclei, neutrons, and electrons defines the physics of the inner crust. The presence of free neutrons alters many properties. One effect is on heat transport. Free neutrons can carry energy differently than electrons or nuclei, and they begin to dominate the thermal conductivity in deeper layers. Another effect is on mechanical properties. The lattice is still rigid, but the free neutrons can move through it, changing how the crust responds to stresses. These neutrons eventually form a superfluid at low temperatures, although that development belongs to later discussion. Even before superfluidity sets in, the mere presence of a neutron sea gives the inner crust distinct behavior compared with the outer crust. As density increases further, nuclei become larger and stranger. They swell with neutrons and their shapes change under the combined influence of nuclear forces and compression. At intermediate depths in the inner crust, nuclei may resemble large drops of nuclear matter suspended in the neutron sea. The spacing between them shrinks as pressure increases. Because the electrons are still present in large numbers, the charge neutrality of the matter is preserved, but the overall character of the material is becoming less like ordinary matter and more like a continuous fluid. The onset of neutron drip also has implications for the star's observable behavior. One important link is to pulsar timing irregularities. The free neutrons of the inner crust will later form a superfluid, and this superfluid is thought to be connected to sudden changes in rotation rate known as glitches. Thus, the neutron drip marks not only a structural boundary, but also the beginning of processes that will influence the dynamics of the star. Nuclear physics experiments help provide guidance for this regime. While no laboratory can reproduce the densities of a neutron star crust, accelerators can create neutron-rich isotopes and probe their stability. By observing how far nuclei can be pushed toward neutron excess before they become unstable, physicists estimate the conditions at which neutrons would drip out in astrophysical environments. These data are folded into models that describe the inner crust. Another way to understand the neutron drip transition is through the balance of forces inside nuclei. Protons and neutrons are held together by the strong nuclear force, which is attractive at short distances but repulsive at very close contact. Neutrons themselves are uncharged, so the main limit on adding them to a nucleus is not electrostatic repulsion, but the saturation of nuclear forces. When too many neutrons are present, some must occupy higher energy states that are less bound. At sufficiently high density, the chemical potential of neutrons outside the nucleus becomes equal to or lower than that inside. At that point, neutrons begin to flow out, leading to the drip. This balance is sensitive to the details of nuclear interactions, which are still subjects of active research. The result is that the exact depth and behavior of the neutron drip layer carry uncertainties, but the general concept is well established. The inner crust extends for about 1 kilometer beneath the surface, and the neutron drip zone is its gateway. This makes it both structurally important and observationally significant. It is within this layer that the properties of matter shift from being dominated by nuclei and electrons to being dominated by a continuous mixture with free neutrons. The crust is no longer purely solid in character, but becomes a hybrid of solid and fluid components. Thermal evolution of neutron stars depends strongly on the behavior of this region. When the star cools, the inner crust regulates the flow of heat from the core to the surface. The free neutrons affect how energy is stored and transmitted. Neutrino emission processes, though weaker here than in the core, also depend on the presence of free neutrons. Observations of cooling curves, particularly of neutron stars that undergo accretion and then relax, have been used to test models of the inner crust. Data show that some stars cool more quickly than others, suggesting variations in crust composition and neutron mobility. The neutron drip point thus connects microscopic nuclear physics with macroscopic astrophysical measurements. Another aspect of the neutron drip transition is its influence on the star's magnetic field. Because electrons provide the main electrical conductivity, they still anchor the magnetic field lines in the crust. However, the added presence of free neutrons changes the mechanical coupling between the magnetic structure and the solid lattice. When stresses build up in the crust due to magnetic pressure, the ability of neutrons to flow modifies how the crust responds. This can influence the likelihood of fractures or shifts events that may be observed as magnetoflares. The concept of a neutron sea may sound abstract, but it is grounded in precise physics. Just as water vapor condenses when pressure increases, nuclear matter reaches a condensation point for neutrons when density becomes high enough. The key difference is that this condensation occurs not by cooling, but by compression, and the result is a fluid of neutrons that can coexist with nuclei in ways not possible under ordinary conditions. In later layers, this neutron sea will dominate, but even at its onset, it changes the basic character of matter. In terms of density, the neutron drip layer is a narrow boundary compared with the overall radius of the star. Yet in terms of physics, it marks a boundary as sharp as the difference between liquid and solid on Earth. Above it, matter is still composed of discrete nuclei and electrons. Below it, matter is a mixture where free neutrons play an essential role. The inner crust begins here, and with it the physics of superfluidity, entrainment, and dynamic coupling that shape much of what makes neutron stars unique. As matter is compressed deeper into the inner crust of a neutron star, the nuclei that make up the lattice undergo further transformations. At lower densities, these nuclei remain roughly spherical, but as density increases toward the base of the inner crust, the balance between nuclear attraction and Coulomb repulsion becomes unstable. Under these conditions, nuclei stretch and deform into unusual geometries. Instead of remaining as compact clusters, they may elongate into rods, flatten into slabs, or arrange into shapes that resemble sheets, tubes, or bubbles. These structures are collectively referred to as nuclear pasta, because of their resemblance to familiar forms of food such as spaghetti, lasagna, or gnocchi. The term is informal, but the physics it describes is precise. Nuclear pasta arises when matter is so dense that nuclei are close enough to feel strong interactions from their neighbours, yet not dense enough to merge completely into uniform nuclear matter. The system minimizes energy by adopting intermediate structures where protons and neutrons cluster in shapes that balance nuclear forces with electrostatic repulsion and the pressure of surrounding electrons. These arrangements are predicted to occur at densities approaching 1/3 of nuclear saturation density, which is about 2 × 10⁻14 grams per cubic centimeter. In this regime, the free neutrons that first appeared at the neutron drip point are abundant. They surround and permeate the pasta structures, forming a fluid background. The lattice is no longer a simple 3-dimensional crystal of spherical nuclei, but an extended network of complex geometries. These shapes influence many physical properties. For example, the geometry affects how neutrinos scatter as they pass through the crust. Because neutrinos interact with nuclei, the extended shapes of nuclear pasta can increase the scattering cross-section compared with spherical nuclei. This means that neutrino transport, which controls cooling in young neutron stars, is altered in the pasta layer. Another effect is on mechanical strength. Calculations suggest that nuclear pasta is one of the strongest materials in the universe, able to withstand stresses much greater than terrestrial metals. This is because the extended shapes interlock, making the structure extremely resistant to deformation. Such strength may help anchor the magnetic field and resist starquakes, although when fractures do occur, the release of energy can be enormous. The pasta phase also has consequences for conductivity. The presence of extended nuclear structures alters how electrons move through the crust. Instead of scattering only off isolated nuclei, electrons encounter rods, slabs, or sheets that create collective scattering patterns. This changes both electrical and thermal conductivities. Since the outer crust and atmosphere depend on how heat is conducted from below the pasta layer, indirectly influences the surface radiation observed by telescopes. These connections mean that even though the pasta layer lies kilometers beneath the surface, its properties may leave signatures in observable data. Theoretical studies of nuclear pasta rely on large-scale simulations, often using molecular dynamics, methods adapted for nuclear forces. These simulations place thousands of nucleons in a box and evolve their interactions under the combined strong and electromagnetic forces. Results consistently show the emergence of non-spherical structures at densities predicted for the base of the inner crust. While direct experimental verification is impossible, analogies can be drawn from complex systems studied in condensed matter physics, where competing forces produce similar patterns of rod sheets and bubbles. The robustness of the prediction across different computational methods gives confidence that nuclear pasta is real, even if its detailed properties remain uncertain. Observational consequences of nuclear pasta are subtle, but potentially detectable. One proposed signature is the timing noise in pulsars. Because nuclear pasta influences the rigidity and viscosity of the inner crust, it may affect how the superfluid component couples to the solid lattice, which in turn influences rotational stability. Another possible signature is in the thermal evolution of cooling neutron stars. If the pasta layer reduces thermal conductivity, it would delay the flow of heat from the core to the surface, altering the cooling curve. Comparing observed cooling data with theoretical models may therefore provide indirect evidence of the pasta phase. Neutrino scattering in nuclear pasta also has relevance for core collapse supernovae where neutrino transport is critical. Although neutron star crusts are cooler and older than supernova environments, the same nuclear structures may appear under similar densities. Thus, understanding pasta has importance beyond neutron stars themselves. The presence of nuclear pasta raises interesting questions about the continuity between different phases of matter inside the star. Above this layer, matter consists of discrete nuclei in a lattice. Below it, matter transitions toward uniform nuclear matter in the core. The pasta shapes are a bridge between these extremes where matter is not entirely discrete nor entirely continuous. In that sense, they represent an intermediate state in the progression from outer crust to core. The free neutrons that surround the pasta structures play an active role. They seep into the geometries filling spaces between rods and slabs. At low temperatures, they form a quantum condensate, making the environment even stranger. The coexistence of quantum superfluid neutrons with rigid pasta shapes is a unique condition, one that challenges the boundaries of known physics. From the perspective of astrophysical modeling, uncertainties remain. Different nuclear interaction models predict different ranges for where pasta appears and what forms dominate. Some models suggest that rods and slabs are most stable, while others predict more complex geometries. The exact thickness of the pasta layer is uncertain, with estimates ranging from a few hundred meters to nearly a kilometer. Despite these variations, the consensus is that some form of pasta must occur before the transition to uniform nuclear matter. The mechanical and thermal consequences are sufficiently strong that they cannot be ignored in realistic neutron star models. Nuclear pasta also illustrates how neutron star interiors blend concepts from different areas of physics. The same interplay between short-range attraction and long-range repulsion that creates pasta shapes in the crust also produces patterns in soft condensed matter systems such as polymers and liquid crystals. This suggests that universal principles of structure formation apply across scales from everyday materials to dense nuclear matter. Recognizing this connection helps physicists draw intuition, though the energies and forces involved in neutron stars are orders of magnitude greater. As the inner crust deepens toward the outer core, pasta gradually gives way to uniform nuclear matter. At that boundary, the nuclei dissolve completely, leaving behind a fluid of neutrons, protons, and electrons. The pasta layer is therefore the final stage in the existence of discrete nuclear structures. Beyond it lies the realm where superfluid neutrons and superconducting protons dominate. This marks the next transition in the interior of the neutron star, one that will be explored by examining the emergence of quantum condensates in the outer core. Deeper inside the neutron star, past the nuclear pasta region, the environment becomes dominated by free neutrons. At these densities, nuclei have dissolved almost entirely, leaving matter in a nearly uniform mixture of neutrons, with a small fraction of protons and electrons. In this regime, the neutrons undergo a remarkable transformation. They form a quantum superfluid. A superfluid is a phase of matter in which particles condense into a single collective state that can flow without viscosity. On Earth, superfluidity is seen in helium at cryogenic temperatures, but in neutron stars it occurs at densities trillions of times greater and at temperatures measured in millions of degrees. The explanation lies in the pairing of neutrons. Just as electrons in certain materials form pairs that give rise to superconductivity, neutrons in dense matter can form pairs through attractive components of the nuclear force. When the temperature falls below a critical threshold, these pairs condense into a macroscopic quantum state, producing superfluid behavior. The critical temperature for neutron superfluidity is on the order of 1 billion degrees, and since neutron stars cool below this threshold within a few years after birth, superfluidity becomes a standard feature of their interiors. The presence of a superfluid alters nearly every property of the star. One of the most striking consequences is the formation of quantized vortices. In ordinary fluids, rotation can be distributed smoothly. In a superfluid, however, rotation is only possible through the creation of discrete vortex lines, each carrying a fixed amount of circulation. In a neutron star, millions of such vortices thread the superfluid region, arranged in a dense array aligned with the rotation axis. The spacing between vortices is microscopic, but collectively they store the angular momentum of the superfluid. Their interactions with the surrounding lattice or with magnetic flux tubes in the proton superconductor play a central role in the rotational dynamics of the star. Another effect of superfluidity is the suppression of certain scattering processes. In normal matter, particles can collide and exchange energy, producing viscosity and resistivity. In a superfluid, these processes are limited by the existence of an energy gap associated with pairing. This reduces the ability of neutrons to exchange energy, lowering viscosity and altering thermal conductivity. It also suppresses some neutrino emission channels, while introducing new ones such as the breaking and formation of neutron pairs, which release neutrinos efficiently. Thus, superfluidity not only governs the mechanical behavior of the star, but also contributes to its cooling. Observational evidence for neutron superfluidity comes indirectly from pulsar glitches. These are sudden increases in the rotational frequency of a pulsar followed by a gradual relaxation back to its earlier trend. The prevailing interpretation is that vortices in the neutron superfluid become pinned to the crust or to other structures, preventing the superfluid from spinning down as the rest of the star loses angular momentum. Over time, a difference builds between the rotation of the superfluid and the crust. When vortices suddenly unpin and move outward, they transfer angular momentum to the crust, producing the observed glitch. The recovery after the glitch reflects the gradual recoupling of the superfluid and the crust. Without superfluid neutrons, such behavior would be difficult to explain. Thermal observations also support the presence of superfluidity. The cooling curve of the neutron star in the Cassiopeia, a supernova remnant, shows a sudden decline in surface temperature over a decade. This rapid cooling is consistent with the onset of neutron superfluidity in the core, which triggers enhanced neutrino emission through pair breaking and formation. The data match models where a large fraction of neutrons become superfluid at the expected temperature. This provides some of the best evidence that neutron superfluidity is not only a theoretical prediction, but a reality inside neutron stars. The physics of neutron superfluidity depends on the type of pairing. At lower densities, neutrons pair in the singlet state, where spins are opposite and the orbital angular momentum is zero. This is called S-wave pairing, and it dominates in the inner crust and outer core. At higher densities, where interactions change, neutrons may pair in triplet states with non-zero angular momentum, leading to P-wave pairing. The critical temperature and gap structure differ between these channels, and this affects neutrino emission and heat capacity. Determining which pairing dominates at which density remains an active area of research, with significant implications for the thermal and rotational evolution of neutron stars. Superfluidity also influences the star's response to oscillations. In normal matter, sound waves and shear modes propagate in familiar ways. In a superfluid, new modes appear due to the relative motion between superfluid and normal components. These include second sound, where temperature waves propagate through the medium. In the astrophysical context, these modes contribute to oscillation spectra that may someday be detectable through gravitational waves. Understanding them requires detailed modeling of superfluid hydrodynamics in curved spacetime. The coexistence of superfluid neutrons with other components complicates the picture further. Protons, though a minority, are present and tend to form a superconducting condensate. Electrons remain as a relativistic gas. The interplay between superfluid neutrons superconducting protons and degenerate electrons defines the structure of the outer core. In particular, vortices in the neutron superfluid interact with magnetic flux tubes in the proton superconductor. These interactions affect how angular momentum and magnetic fields evolve, coupling rotational and magnetic phenomena in ways not yet fully understood. From a mechanical perspective, the rigidity of the crust above and the fluidity of the superfluid below create conditions for unique phenomena. Vortices may pin to the crust, storing stress until they suddenly unpin. They may also interact with nuclear pasta at the crust base, further complicating their dynamics. These microphysical interactions scale up to observable events like glitches and timing irregularities. Thus, superfluidity connects microscopic quantum mechanics with macroscopic astrophysical behavior. Experiments on Earth cannot reproduce neutron superfluidity under such densities, but analogies exist. Studies of ultra-cold atomic gases where fermions are cooled to nanokelvin temperatures show pairing and superfluidity under controlled conditions. Though densities differ by many orders of magnitude, the underlying principles of pairing and condensation are the same. Insights from these experiments inform theoretical treatments of neutron star matter, bridging the gap between laboratory physics and astrophysical extremes. The existence of neutron superfluidity also raises questions about dissipation. While superfluids flow without viscosity, they still exchange energy through interactions with their environment. In a neutron star, vortices moving through the crust or magnetic structures create mutual friction, a dissipative mechanism that affects rotational stability. The strength of this mutual friction depends on details of vortex pinning and drag which are still uncertain. Different models predict different levels of coupling between the superfluid and the rest of the star, leading to variations in predicted glitch behavior. Future observations may help constrain these models. Overall, the presence of superfluid neutrons in the outer core and inner crust is one of the defining features of neutron star interiors. It transforms the behavior of matter from a rigid lattice of exotic nuclei to a quantum condensate, with vortices, altered thermal properties, and unique observational signatures. The study of this phase continues to reveal how the fundamental forces of nature operate under densities and pressures unattainable elsewhere, linking nuclear physics, condensed matter, physics and astrophysical observation into a single framework. In the dense outer core of a neutron star, the minority population of protons takes on a role just as remarkable as the superfluid neutrons. Although neutrons make up the majority of the matter, a small fraction of protons, typically a few % of the total baryon content, is present to balance charge along with electrons and sometimes muons. At the immense densities and relatively low temperatures that exist inside the star, these protons form pairs similar to how electrons in terrestrial superconductors pair up in what is called the Cooper mechanism. Once paired, the protons condense into a collective state that conducts electric current with zero resistance. This phenomenon is known as superconductivity. In a neutron star, the superconducting state is even stranger than in laboratory materials, because the environment is dominated by nuclear interactions, relativistic effects, and strong gravitational fields. The critical temperature for proton superconductivity is extremely high compared to human experience, on the order of billions of degrees, as neutron stars cool quickly below these temperatures in their early life. The conditions for superconductivity are established almost universally in their cores. The superconducting protons coexist with superfluid neutrons, creating a complex dual condensate that shapes the entire dynamics of the star. Unlike neutrons, protons carry electric charge, so their superconductivity directly influences the magnetic field. In a Type I superconductor, magnetic fields are expelled completely, but in a Type II superconductor, magnetic fields thread through the material in quantized flux tubes. Calculations and models suggest that the proton condensate in neutron stars is a Type II superconductor. This means that the magnetic field does not vanish inside the core, but instead organizes itself into an immense array of thin filaments, each carrying a fixed quantum of magnetic flux. These flux tubes are spaced at microscopic intervals, but collectively they contain the entire magnetic field of the star. The arrangement of flux tubes interacts with the vortex lattice of the neutron superfluid. Vortices and flux tubes can become entangled, pinning to one another and influencing both rotation and magnetism. This coupling may be one of the key ingredients in explaining observed pulsar phenomena such as glitches, timing noise, and long-term spin evolution. The superconducting state also alters the way electric currents flow. In normal matter, resistance causes currents to decay with time. In a superconductor, currents can persist indefinitely without loss. Thus, the currents that generate a neutron star's magnetic field can remain stable for millions of years. This helps explain why pulsars maintain strong magnetic fields over astronomical timescales. Without superconductivity, resistive decay would weaken the field much more quickly than observed. The superconducting protons also influence heat transport. While electrons are still the main carriers of thermal conductivity, the pairing of protons modifies the density of states available for scattering. This reduces the contribution of protons to heat capacity and alters neutrino emission processes. In particular, pair breaking and formation of protons can release neutrinos just as it does for neutrons. These neutrino processes accelerate cooling at specific times, producing features in the thermal evolution of the star. Observations of young neutron stars have been compared with models that include proton superconductivity, and the agreement supports the presence of this state. Another important role of proton superconductivity is in stabilizing the star against instabilities. In a rotating neutron star, fluid oscillations called R modes can grow and emit gravitational waves. The damping of these oscillations depends on internal viscosity and mutual friction. Superconducting protons, by altering the coupling between charged and neutral components, help determine the stability of these modes. Thus, superconductivity is not only a microscopic phenomenon, but one with macroscopic consequences for gravitational wave emission. From a theoretical standpoint, the strength of proton pairing depends on the density and the details of nuclear interactions. At lower densities, singlet pairing dominates, while at higher densities, pairing may weaken or shift to different channels. The exact density range where superconductivity persists remains uncertain, with different models giving different boundaries. Nevertheless, it is widely accepted that a significant region of the outer core is superconducting. Laboratory experiments on Earth cannot replicate these conditions directly, but analogies exist with ultra-cold fermionic systems and with metallic superconductors studied in condensed matter physics. These comparisons provide insight, though the extrapolation to nuclear densities is extreme. Superconducting protons also affect the star's response to external perturbations. For example, when a neutron star accretes matter from a companion, the magnetic field can be buried or distorted. The superconducting core resists such changes, causing the field to re-emerge over long timescales. Similarly, during magnetar outbursts, stresses in the crust may disturb the magnetic field configuration, but the flux tube lattice in the core provides an anchoring framework that regulates the field's recovery. Observational evidence for proton superconductivity is indirect but persuasive. Cooling curves of neutron stars require both neutron superfluidity and proton superconductivity to match data. Theoretical models without superconductivity fail to reproduce observed rapid cooling episodes. Additionally, the persistence of strong magnetic fields in old pulsars suggests that resistive decay is suppressed, consistent with superconducting currents. While no direct measurement can yet confirm superconductivity in neutron stars, the convergence of theory and observation strongly supports its existence. The interaction between proton superconductivity and neutron superfluidity remains one of the central puzzles of neutron star physics. Vortices in the neutron superfluid may pin to proton flux tubes coupling the rotational and magnetic evolution of the star. If vortices move relative to flux tubes, frictional processes occur, dissipating energy and affecting spin stability. These microphysical interactions are thought to underlie phenomena such as pulsar glitches, timing noise, and possibly gravitational wave signals. Understanding them requires complex modeling, and many details remain uncertain. The coexistence of these two condensates makes the outer core of a neutron star one of the richest laboratories for quantum many-body physics in the universe. Proton superconductivity also plays a role in neutrino emission beyond pair processes. In regions where superconductivity suppresses scattering, some neutrino channels are reduced, changing the balance of cooling. The overall thermal history of the star therefore depends sensitively on where and how proton superconductivity exists. Astronomers continue to refine cooling models using data from X-ray observatories to constrain the properties of dense matter. In sum, the superconductivity of protons in the outer core is a natural consequence of the same pairing principles seen in condensed matter physics, but it occurs under densities and conditions far beyond terrestrial reach. It stabilizes magnetic fields, alters cooling shapes, rotational dynamics, and provides indirect evidence through observations. It also couples intimately with neutron superfluidity, making the physics of the neutron star core an inseparable web of quantum states. By understanding superconducting protons, scientists gain a clearer picture of how neutron stars maintain their extraordinary properties over millions of years, linking microscopic quantum rules to the astrophysical behavior observed across the galaxy. Alongside the neutrons and protons that dominate the outer core of a neutron star, leptons provide the essential balance of charge and pressure that keeps the system in equilibrium. Leptons are particles such as electrons and muons that do not experience the strong nuclear force but do respond to the electromagnetic and weak forces. Their role is crucial because the number of protons in the star is small compared with the number of neutrons, and the overall matter must remain electrically neutral. Electrons supply this neutrality by balancing the positive charge of protons. Because the density inside the core is enormous, electrons are squeezed into a degenerate gas similar to the electrons in the crust, but at even higher energies. At such densities, the Fermi energy of the electrons rises to values so high that the electrons move at speeds close to that of light. In this relativistic state, the pressure provided by the electron gas contributes significantly to supporting the star against gravity. The presence of electrons also allows certain weak interaction processes such as beta decay and its inverse to operate and maintain chemical equilibrium between neutrons, protons and leptons. As density increases further, another lepton species becomes energetically favorable, the muon. Muons are heavier cousins of electrons with about 200 times the mass. Under normal terrestrial conditions, muons are unstable and decay quickly into electrons and neutrinos. Inside a neutron star, however, the conditions are different. Once the electron chemical potential exceeds the rest mass of a muon, it becomes energetically possible to replace some electrons with muons. This transition happens when the density reaches several times nuclear saturation density. At that point, muons appear in significant numbers coexisting with electrons and sharing the task of balancing proton charge. The presence of muons modifies the equilibrium of the core. They reduce the pressure carried by electrons, redistribute energy states, and open additional channels for neutrino emission. Although muons are heavier, they behave as degenerate fermions in the same way as electrons. They fill up energy states according to the exclusion principle and contribute to the overall lepton pressure. The coexistence of electrons and muons ensures that the proton fraction remains small but stable, preventing runaway processes that would otherwise destabilize the system. This equilibrium is called beta equilibrium, a state in which the rates of beta decay and inverse beta decay balance. In this state, neutrons can convert to protons and electrons if it lowers energy, and protons can capture electrons to become neutrons if that is favored. The inclusion of muons extends these reactions since protons can capture muons as well. The equilibrium composition is thus a finely tuned balance between the three baryon and lepton species, governed by the chemical potentials of each. The presence of leptons also has consequences for transport properties. Electrons and muons are the primary carriers of electric current since neutrons are neutral, and protons are bound in a superconducting state. This means that leptons determine how the magnetic field evolves inside the star. In the superconducting proton medium, magnetic fields thread as flux tubes, but the overall electrical conductivity is shaped by the leptons. Because they are relativistic and degenerate electrons in particular, provide extremely high conductivity, effectively freezing magnetic fields into the matter for long timescales. This helps explain why pulsars and magnetars retain their magnetic fields for millions of years despite processes that might otherwise lead to decay. Thermal conduction is also strongly affected by leptons. Both electrons and muons transport heat efficiently, carrying energy across large distances without much scattering. This makes them central to the cooling history of neutron stars. Heat generated in the core is conducted outward by leptons and then radiated away from the surface as photons or neutrinos. If lepton transport were less efficient, cooling curves would look very different from those observed. Astronomers use X-ray observations of neutron stars to compare surface temperatures with models of interior cooling, and these comparisons rely on accurate descriptions of lepton behavior. Another role of leptons is in neutrino emission. Neutrinos are ghost-like particles that escape freely from the dense star, carrying away energy. Many neutrino emission processes involve leptons. For example, the modified Urca process requires the presence of electrons to conserve momentum when neutrons convert to protons and emit neutrinos. If the proton fraction is high enough, the direct Urca process can operate in which neutrons convert directly to protons and electrons while emitting neutrinos. The threshold for direct Urca depends on the fraction of protons and hence on the balance with leptons. If muons are present, additional direct Urca processes involving muons become possible, accelerating cooling even further. Thus, the lepton content of the core controls which neutrino processes dominate, and therefore how quickly the star loses heat. The distinction between modified and direct Urca channels is not just a theoretical detail. It has observable consequences. Stars with direct Urca operating cool much faster than those limited to modified Urca. Observed temperature differences between neutron stars of different masses can therefore be explained if some stars have conditions that allow direct Urca while others do not. The presence of muons broadens the range of stars that might undergo rapid cooling, making lepton physics directly relevant to observations. Another interesting aspect of leptons in neutron stars is their interaction with magnetic fields. In strong magnetic fields, such as those of magnetars, the motion of charged particles perpendicular to the field becomes quantized into discrete energy levels known as Landau levels. Electrons, being lighter, are more strongly affected than muons. This quantization changes the density of states and can alter pressure, conductivity, and neutrino emission. In extreme fields, only the lowest Landau levels may be populated, leading to highly anisotropic transport properties. Such conditions are difficult to model, but they provide one possible explanation for unusual emission behaviors seen in magnetars. The importance of leptons is further emphasized by their role in charge screening. Protons repel each other through electrostatic forces, and without leptons to neutralize these charges, the system would be unstable. Electrons and muons form a background that screens these interactions, allowing protons to coexist in a stable mixture. This screening effect influences not only equilibrium, but also how collective oscillations propagate. For instance, Alfvén waves, which are magnetohydrodynamic oscillations in a plasma, are modified by the presence of leptons. These waves may contribute to the quasi-periodic oscillations observed in magnetar flares, linking microscopic lepton physics to macroscopic signals. Experimental input on lepton behavior at such densities is limited, but theoretical treatments rely on well-understood quantum electrodynamics. The challenge is not the basic physics of electrons or muons, but their interaction with nuclear matter at extreme densities. High-energy astrophysics observatories such as NICER Chandra and XMM Newton provide indirect tests of these models by measuring surface temperatures, cooling curves, and timing properties. By comparing these data with simulations that include detailed lepton physics, researchers refine their understanding of how electrons and muons operate in the core. The role of leptons may seem secondary compared to the dramatic phenomena of superfluid neutrons and superconducting protons, but without them the entire structure would collapse into imbalance. They provide neutrality, regulate cooling, transport heat, stabilize magnetic fields, and set thresholds for neutrino processes. In the complex web of physics inside neutron star cores, leptons are the quiet but essential participants that ensure the system remains balanced and observable. The cooling of a neutron star is governed primarily by the emission of neutrinos particles that interact only weakly with matter and therefore escape almost unhindered from the dense interior. From the moment a neutron star is born in a supernova, it begins to lose energy, first through neutrino radiation from the core, and later when the star is cooler, through photon emission from the surface. Neutrino processes dominate during the first 100,000 years, and their details depend directly on the microphysics of the dense matter inside the star. Several channels are important, each with distinct conditions and rates. The simplest is called the direct Oerker process. In this channel, a neutron decays into a proton, an electron, and an antineutrino, while the reverse process sees a proton and an electron combine into a neutron and a neutrino. These reactions are very efficient at removing energy, but they require that momentum can be conserved among all participating particles. That requirement imposes a threshold on the fraction of protons in the matter. Only if the proton population is sufficiently large can direct Oerker occur. Models show that this threshold is reached only at higher densities, which means that direct Oerker operates only in the cores of the most massive neutron stars. Where direct Oerker is forbidden, the star cools more slowly through other channels. The most important of these is the modified Oerker process. It involves the same basic reactions as direct Oerker, but requires the presence of a bystander nucleon, either a neutron or a proton, to absorb momentum and allow the reaction to proceed. This extra step makes modified Oerker much less efficient than direct Oerker, but it can occur under a wide range of conditions and therefore dominates in stars that do not meet the threshold for direct Oerker. Modified Oerker reactions steadily drain energy through neutrino emission during the early life of the star. A third class of neutrino emission arises when nucleons form pairs. When neutrons or protons pair into superfluid or superconducting states, they release energy in the form of neutrinos during both the creation and the breaking of pairs. This pair breaking and formation process is particularly important during the onset of superfluidity or superconductivity. As the temperature drops below the critical point for pairing, large numbers of pairs are created, and each creation releases neutrinos. This leads to a burst of cooling, often visible in models as a sharp decline in temperature. Observations of the neutron star in Cassiopeia show evidence of such a cooling burst, providing strong support for the reality of superfluid and superconducting phases. The efficiency of neutrino emission also depends on the presence of muons. When muons appear at high density, additional direct and modified Oerker processes involving muons become possible. These reactions accelerate cooling further. The presence or absence of muons can therefore change the cooling behavior of stars of similar mass. Observations of neutron stars with different temperatures and ages suggest a diversity of cooling rates, consistent with variations in internal composition and neutrino processes. Another class of neutrino emission mechanisms involves Bremsstrahlung, where particles scatter off one another and emit neutrino pairs. In the dense neutron fluid, neutron-neutron scattering can produce neutrinos, though at a lower rate than Oerker processes. Electron nucleus scattering in the crust also produces neutrinos, contributing to cooling at intermediate stages. These processes are less dominant but still play a role in the overall energy budget. Neutrino emission is not only a mechanism for cooling, but also a diagnostic of the star's interior. By comparing observed surface temperatures with theoretical cooling curves, astronomers can infer which processes are active. If a star cools rapidly, it suggests that direct Oerker or strong pair-breaking processes are operating. If it cools more slowly, modified Oerker and weaker processes dominate. These comparisons provide one of the few observational windows into the physics of dense matter. The cooling curve of Cassiopeia A is especially instructive. Data from Chandra X-ray Observatory over a decade revealed a decline in surface temperature, consistent with enhanced neutrino emission. The interpretation is that neutrons in the core became superfluid at that time, triggering pair breaking and formation neutrinos. This observation matches theoretical predictions and strongly indicates that superfluidity is a real feature of neutron star interiors. Cooling observations also reveal differences between neutron stars of different ages. Young neutron stars, a few thousand years old, radiate strongly in X-rays, and their surface temperatures are set by internal cooling. Middle-aged neutron stars around 100,000 years old are cooler, and their emission is weaker, consistent with neutrino processes declining and photon emission from the surface becoming dominant. Very old neutron stars, millions of years in age, cool mainly through surface photon radiation, since the core has become too cold for strong neutrino emission. In addition to isolated neutron stars, accreting systems provide insight. In transient X-ray binaries, neutron stars accrete matter episodically, heating their crusts through nuclear reactions. When accretion halts, the star cools, and the rate of cooling is measured through X-ray observations. These crustal cooling curves reflect both crust properties and core neutrino processes. By fitting these curves, astronomers constrain thermal conductivity, heat capacity, and neutrino emissivity. In particular, they show that rapid neutrino cooling must occur in some stars consistent with direct Urca or similar efficient processes. The physics of neutrino emission is closely tied to the nuclear equation of state. The proton fraction, which determines whether direct Urca is possible, depends on the symmetry energy of nuclear matter. This symmetry energy describes how the energy of nuclear matter changes when the ratio of neutrons to protons changes. Different theoretical models predict different symmetry energies and therefore different proton fractions. Observational evidence of rapid cooling can therefore be used to test nuclear interaction models. Neutrino emission also influences rotation and magnetic evolution indirectly. As the star cools, the properties of superfluid and superconducting phases change. The density of vortices and flux tubes, their pinning and motion all depend on temperature. Thus, the history of cooling sets the stage for later dynamical behavior. Neutrino emission is therefore not only an endpoint of energy loss, but also a regulator of the internal state of the star. Experimental studies of neutrinos on Earth provide complementary insight. Neutrino detectors such as Super Kamiokande and IceCube measure neutrinos from the Sun from cosmic rays, and potentially from supernovae. While these detections do not probe neutron stars directly, they refine our understanding of weak interaction processes, which are the same processes operating inside neutron stars. The detection of neutrinos from supernova 1987A confirm that neutrino emission is the dominant channel of energy loss in stellar collapse. The same principle applies to neutron star cooling, although on longer timescales. Future detections of neutrinos from a nearby supernova could provide direct evidence of the formation and early cooling of a neutron star, offering an unprecedented test of theory. In summary, within this section, neutrino emission channels such as modified Urca, direct Urca, and pair breaking and formation govern the thermal history of neutron stars. Their efficiency depends on composition density and pairing states, and their observational signatures provide critical clues to the microphysics of dense matter. By studying cooling curves, burst behaviors, and transient systems, astronomers continue to refine the picture of how these faint particles silently shape the evolution of some of the densest objects in the universe. The magnetic field of a neutron star is one of its most striking features, and its behavior inside the dense core depends closely on the presence of superconducting protons and degenerate leptons. Magnetic fields in ordinary stars are carried by electric currents in plasma, but inside a neutron star the plasma is transformed into exotic states. The protons in the outer core form a type II superconductor, meaning that the magnetic field cannot penetrate smoothly, but is instead confined into quantized flux tubes. Each flux tube carries a single quantum of magnetic flux, and together they form a dense lattice threading through the superconducting region. The density of these flux tubes is enormous. For a magnetic field of 1 trillion Gauss, which is typical of pulsars, the spacing between flux tubes is on the order of a few hundred femtometers smaller than the size of most nuclei. In magnetars, where fields can reach 1 quadrillion Gauss, the flux tube lattice is even denser. This microscopic structure underpins the large-scale magnetic behavior seen in observations. The flux tube lattice does not exist in isolation. It interacts with the array of neutron vortices formed by the rotating superfluid. Because both vortices and flux tubes are linear structures aligned roughly with the rotation axis, they can cross and entangle. Their interaction is a source of coupling between rotation and magnetism. If vortices pin to flux tubes, the motion of the superfluid becomes tied to the magnetic field structure, affecting how angular momentum is transferred during spin-down or glitches. If vortices cut through flux tubes, frictional processes occur, dissipating energy and altering rotational stability. This dynamic interplay is one of the central unsolved problems of neutron star physics. The presence of a superconducting core also affects how magnetic fields evolve over long time scales. In normal matter, magnetic diffusion causes fields to decay as currents dissipate. In a type II superconductor, currents can persist indefinitely, and the flux tubes themselves are stable. However, stresses in the crust and differential rotation can cause flux tubes to move, rearrange, or even expel from the core. The timescale of this motion determines how magnetic fields decay or evolve over millions of years. Observations of pulsars show that fields remain strong for long periods, consistent with the idea that superconductivity suppresses rapid decay. In magnetars, the situation may be more complex. Their extremely strong fields may stress the crust beyond its breaking point, causing fractures and bursts of radiation. The field configuration in magnetars may involve both crustal currents and core flux tubes, and their interaction may drive the episodic activity. For example, sudden shifts in flux tube arrangement could transmit stresses to the crust, leading to starquakes and flares. Magnetic geometry inside neutron stars is not uniform. Near the surface field lines can be twisted or tangled, especially in magnetars. Inside the core, however, the superconducting state organizes the field into an orderly array of flux tubes. This dual structure raises questions about how the outer and inner field configurations are connected. The transition between crustal fields and core fields may involve complex boundary layers where superconductivity, normal matter, and nuclear pasta meet. Modeling these transitions is a challenge, but they are critical for understanding how internal field evolution connects to observable emission. The effect of magnetic fields on particle motion is profound. Electrons and muons in strong magnetic fields occupy discrete Landau levels, changing their density of states and altering pressure and transport. In magnetars, the field strength is so extreme that only the lowest Landau levels may be populated, producing anisotropic behavior. This influences neutrino emission heat conduction and the equation of state. Such modifications can affect cooling rates and the structure of bursts, adding further complexity to the observational picture. Magnetic fields also couple to oscillation modes of the star. In highly magnetized stars, oscillations of the crust or core can excite magnetohydrodynamic waves along field lines. These waves may appear as quasi-periodic oscillations observed in the tails of magnetar flares. If so, they provide a rare window into the magnetic structure of the interior. The frequencies of these oscillations depend on field strength geometry and coupling with the superfluid and superconducting components. Observations from space telescopes such as RXTE and NICA have detected such oscillations, stimulating efforts to model them in detail. The presence of superconductivity complicates magnetic wave propagation. Flux tubes can vibrate and interact with vortices, producing hybrid modes that are not seen in normal plasmas. These modes may dissipate energy into heat or neutrinos, influencing both the thermal and dynamical evolution of the star. Understanding them requires combining quantum mechanics, magnetohydrodynamics, and general relativity in a single framework. Over very long timescales, magnetic field evolution shapes the observable life of neutron stars. Pulsars slow down as their fields carry away rotational energy through electromagnetic radiation. Magnetars flare and release energy stored in twisted magnetic fields. Millisecond pulsars spun up by accretion maintain lower but stable fields that allow precise timing. All of these behaviors depend on how magnetic fields are anchored and evolve in the superconducting core. Without flux tube structures, and high conductivity fields would decay too quickly to match observations. The flux tube lattice is thought to be one of the strongest materials in existence, with enormous tension resisting distortion. Yet it is not immutable. Flux tubes can drift through the superconductor due to buoyancy interactions with vortices or external stresses. Their motion is slow but cumulative, leading to gradual field evolution over millions of years. This slow drift may explain the observed decay of magnetic fields in old neutron stars. Observationally, the distribution of neutron stars across the pulsar and magnetar populations reflects the role of magnetic fields. Some stars retain moderate fields and behave as radio pulsars, while others develop extreme fields and episodic bursts. The reasons for these differences may include initial conditions at birth, differences in accretion history, and variations in superconducting behavior of the core. By studying magnetic properties, astronomers seek to connect surface observations with core physics. Theoretical models of magnetic evolution often include Hall drift and ohmic decay in the crust, but in the core, superconductivity dominates. Including flux tube dynamics is essential for realistic predictions. The complexity of these models shows how deeply intertwined magnetism is with the quantum states of dense matter. Laboratory analogues exist in superconductors studied in condensed matter physics, where flux tubes and vortices interact. Experiments on Type II superconductors show pinning motion and collective behavior of flux tubes phenomena that resemble what is expected in neutron star cores. These analogies provide qualitative insight, though the scales of density and field strength are far beyond human reach. The link between microphysics and astrophysical behavior is clear. Superconducting protons create flux tubes. Flux tubes interact with neutron vortices, and together they shape the rotation, magnetism, and emission of the star. Observational data from X-ray and radio telescopes continue to test these ideas, refining the understanding of how one of the universe's most extreme magnetic environments operates. The rotation of neutron stars is one of their most measurable properties, and it reveals much about the physics of their interiors. Newly formed neutron stars can rotate many times per second, and as they age, they gradually lose rotational energy through electromagnetic radiation and particle winds. The rate of this slowdown or spin down is measured with great precision by radio and X-ray observations. Yet the spin does not always decrease smoothly. Many pulsars experience sudden increases in rotation rate known as glitches. These events provide some of the most direct evidence of the behavior of superfluid neutrons inside the star. In a normal fluid, angular momentum is distributed continuously. In a superfluid, rotation is carried by quantized vortices each a thin tube of circulating flow. The density of these vortices is proportional to the rotation rate, so a faster spinning star contains more vortices. As the neutron star spins down due to electromagnetic torque, vortices must slowly move outward to reduce the rotation of the superfluid. However, vortices are not free to move easily. They can pin to the rigid crust or to magnetic flux tubes in the superconducting proton medium. When pinned vortices are locked in place and the superfluid cannot follow the gradual slowdown of the crust. Over time, a differential builds up between the angular velocity of the crust and that of the superfluid. The crust slows, but the superfluid remains closer to its original speed. Stress accumulates at the pinning sites and eventually vortices unpin, in large numbers moving outward suddenly and transferring angular momentum to the crust. This transfer manifests as a glitch. The crust abruptly spins faster. After the glitch, the system relaxes as vortices repin and the differential rebuilds. Observationally, glitches vary in size from tiny changes of 1 part in a billion to large jumps easily measurable in timing data. The Vela pulsar is a classic example showing frequent large glitches. These events confirm that superfluidity and vortex dynamics play a central role in neutron star rotation. Glitches also reveal information about the strength of vortex pinning and the fraction of the star's moment of inertia contained in the superfluid. The amplitude of glitches implies that a significant portion of the star's interior, possibly several % of its total moment of inertia, participates in the superfluid reservoir. This provides constraints on the thickness of the crust and the distribution of superfluid neutrons. Without superfluidity, it would be difficult to explain the sudden and discrete changes in rotation. Beyond glitches, rotational irregularities include timing noise, a more random wandering of the rotation rate. This noise may arise from complex interactions between vortices, flux tubes, and crustal stresses. While not as discrete as glitches, timing noise still reflects the internal coupling of different components of the star. The precision of pulsar timing makes these small variations detectable, turning neutron stars into laboratories for quantum fluid dynamics under extreme conditions. The interplay between rotation and magnetic fields is also crucial. Vortices in the neutron superfluid and flux tubes in the proton superconductor may pin to each other, linking the rotational dynamics with magnetic evolution. If vortices drag flux tubes as they move, they can redistribute magnetic fields, altering long-term spin down. Conversely, magnetic field structures may impede vortex motion, affecting the frequency and size of glitches. This entanglement of rotation and magnetism is one of the open questions of neutron star physics. Observations of magnetars add another layer. Some magnetars show glitch-like events that coincide with X-ray bursts, suggesting that crustal fractures and magnetic rearrangements can trigger or amplify rotational changes. These multi-messenger signals strengthen the connection between rotation magnetism and the microphysics of the core. Thermal evolution also influences rotational behavior. As the star cools, superfluid and superconducting states develop and expand. The density and mobility of vortices change with temperature, as does the pinning strength to the crust. Young neutron stars may experience different glitch patterns than older, cooler ones. Observational surveys of pulsars at different ages support this idea, with glitch activity evolving over time. Models of rotational dynamics must include temperature-dependent properties to reproduce the data. Another phenomenon connected to rotation is the R-mode instability. These are global oscillations that couple strongly to gravitational wave emission. If R-modes grow, they can rapidly spin down the star by radiating angular momentum away. The stability of R-modes depends on viscosity and mutual friction, both of which are controlled by superfluid and superconducting properties. Proton superconductivity, lepton scattering, and vortex dynamics all contribute. While no direct detection of R modes has been made, gravitational wave observatories such as LIGO and Virgo have searched for signals from rapidly rotating neutron stars. The absence of strong signals places constraints on the damping mechanisms inside the core. Experiments on Earth help provide analogies for vortex behavior. Studies of superfluid helium and ultra-cold atomic gases show how vortices form, move, and interact. Pinning, unpinning, and vortex avalanches have been observed in laboratory systems, lending support to the idea that similar processes occur in neutron stars, albeit on vastly different scales. These analogies help guide theoretical treatments of glitches and timing noise. Observations of pulsar glitches also provide insight into nuclear physics. The fraction of moment of inertia that participates in glitches depends on how strongly neutrons in the crust are entrained by nuclei. If entrainment is strong, fewer free neutrons are available, requiring a thicker crust to explain observed glitch amplitudes. This links pulsar timing data to the equation of state of nuclear matter. In this way, rotational phenomena probe dense matter just as effectively as cooling curves or gravitational wave signals. Glitches also serve as natural experiments in angular momentum transfer. Each event shows how a quantum condensate interacts with a solid lattice under stress. By monitoring many glitches across different pulsars, astronomers build a statistical picture that constrains models of vortex pinning, crust strength, and mutual friction. Future timing campaigns, especially with sensitive radio arrays and X-ray timing observatories, will refine this picture further. In addition to sudden glitches, gradual spin changes such as anti-glitches, where the rotation suddenly slows, have been reported in magnetars. These may result from magnetic torques or crustal motions rather than vortex dynamics, but they highlight the diverse ways in which neutron star rotation can change. Together, glitches, anti-glitches, and timing noise form a spectrum of rotational irregularities that trace the complex interior physics. Over long timescales, rotation provides a chronometer of neutron star evolution. The steady spin down due to magnetic braking sets the age scale, while irregularities superimpose evidence of internal processes. By combining timing data with thermal and spectral observations, scientists build a multi-layered view of neutron star interiors. Each piece of data contributes to a larger picture of how quantum fluids, superconductors, and magnetic structures interact under extreme gravity. In conclusion of this section, the phenomenon of glitches and other rotational irregularities demonstrates that neutron stars are not static remnants, but dynamic systems where quantum mechanics and astrophysical forces intersect. Vortices in superfluid neutrons, their pinning and motion, and their interaction with flux tubes in the crust provide the mechanisms behind observed changes in rotation. Through precise timing observations, these mechanisms become visible, allowing the strange physics of the interior to be inferred step by step. Inside a neutron star, the motion of different components is never completely independent. Neutrons, protons, and electrons interact through a variety of couplings, and when neutrons form a superfluid, their vortices still feel forces from the crust and from other constituents. One of the most important mechanisms governing this interaction is called mutual friction. Mutual friction arises when vortices in the neutron superfluid experience drag from their surroundings. A vortex core can trap normal particles or interact with excitations, and as the vortex moves, it exchanges momentum with the environment. In a neutron star, vortices can scatter electrons through magnetic fields generated by entrained protons, or they can interact directly with nuclei in the crust. Each of these processes slows vortex motion, providing a channel for angular momentum transfer between the superfluid and the rest of the star. This coupling ensures that the rotation of different layers does not drift apart indefinitely. The strength of mutual friction depends on density, temperature, and composition. In the inner crust, vortices thread through a lattice of nuclei. They can pin to nuclei, preventing motion until the stress becomes large, or they can creep slowly by thermal activation, hopping from one pinning site to another. In the outer core, vortices interact with flux tubes in the proton superconductor. If pinning is strong, vortices drag flux tubes with them, coupling neutron and proton components. If pinning is weaker, vortices cut through flux tubes, producing friction and dissipating energy. Both regimes have consequences for rotational dynamics. Mutual friction is central to explaining the post-glitch relaxation seen in pulsars. After a glitch, the star does not remain at its new frequency, but gradually relaxes toward the pre-glitch trend. This relaxation reflects the recoupling of the crust and the superfluid through mutual friction. The timescale of relaxation provides information about the strength of coupling. In some pulsars, recovery is fast, suggesting strong mutual friction, while in others it is slow, pointing to weaker coupling. By analyzing these recoveries, astronomers gain insight into the microphysics of vortex drag. A related concept is entrainment. In nuclear matter, neutrons are not entirely free to move independently of nuclei or protons. Instead, quantum mechanical effects cause some of their momentum to be carried along with the surrounding medium. In the crust, this means that superfluid neutrons are partially locked to nuclei, effectively increasing the mass of nuclei and reducing the number of free neutrons available to flow. This entrainment modifies the distribution of angular momentum in the star. It reduces the fraction of moment of inertia stored in the superfluid and alters glitch dynamics. Observational estimates of glitch sizes combined with entrainment models constrain the thickness and composition of the crust. If entrainment is strong, the crust must be thicker to account for observed glitch amplitudes. In the core, entrainment between neutrons and protons plays a similar role. Superfluid neutrons and superconducting protons can share momentum through nuclear interactions. This affects how they move relative to each other and how magnetic fields couple to rotation. Entrainment also influences oscillations and wave propagation. In a two-fluid system with entrainment, the effective mass of each component differs from its bare mass, leading to modified dispersion relations for sound and other collective modes. These modes could, in principle, be detected through gravitational waves if they are excited in events such as starquakes or binary mergers. Mutual friction and entrainment together form the basis for neutron star hydrodynamics. Unlike ordinary fluids, where viscosity alone controls momentum transfer, here, the presence of superfluidity and superconductivity introduces new channels. The equations describing motion must include vortex dynamics, flux tube interactions, and entrainment coefficients. Solving these equations in realistic geometry is challenging, but progress has been made using both analytic models and large-scale simulations. Observational data continue to provide essential tests. The recovery phases of glitches, the stability of rotation in millisecond pulsars, and the amplitude of timing noise all provide constraints. For example, millisecond pulsars exhibit remarkable rotational stability, suggesting strong coupling between components. This indicates that mutual friction in their cores may be stronger than in slower pulsars. Conversely, large glitches in young pulsars require partial decoupling, implying weaker friction or stronger pinning. Another arena where mutual friction and entrainment matter is in oscillation damping. R-mode instabilities, which can emit gravitational waves, are stabilized if mutual friction is strong. The absence of strong continuous gravitational wave signals from known pulsars suggests that damping is efficient, possibly due to vortex flux tube interactions. Entrainment alters the frequencies of oscillations, shifting them from values predicted by single fluid models. Thus, gravitational wave searches, though not yet yielding direct detections, are already constraining the physics of coupling in neutron star interiors. Laboratory experiments cannot replicate neutron star conditions, but analogies exist. In superfluid helium vortices experience mutual friction with normal fluid components, and entrainment effects are observed in mixtures of helium isotopes. Ultra-cold atomic gases provide further analogies where tunable interactions allow studies of vortex dynamics and entrainment in controlled settings. These laboratory systems help develop intuition and test theoretical frameworks, even though densities and forces differ by many orders of magnitude. The role of mutual friction also extends to thermal evolution. As vortices move and interact, they dissipate energy, contributing to heating. In regions where pinning is strong, sudden unpinning events release stored energy that may appear as bursts of radiation. This is particularly relevant in magnetars where strong magnetic stresses interact with vortex dynamics to trigger flares. The combined effect of vortex unpinning mutual friction and crustal fractures may produce the diverse range of observed phenomena. The study of entrainment connects nuclear physics to astrophysical observables. Entrainment coefficients depend on how neutrons interact with nuclei and protons, quantities determined by the nuclear symmetry energy, and other aspects of the equation of state. By matching glitch data with models, scientists place constraints on these nuclear parameters. In this way, timing measurements of pulsars complement laboratory experiments on neutron-rich nuclei. Over long timescales, mutual friction ensures that the star behaves as a coupled system rather than as independent layers. Without it, differential rotation would grow unchecked, leading to instabilities. With it, angular momentum is redistributed smoothly, allowing the star to evolve coherently. Yet the imperfections in coupling produce the irregularities that make pulsars such valuable probes. Every glitch, every recovery, every small variation in timing is a trace of the hidden friction and entrainment processes at work deep inside. In the broader picture of neutron star physics, mutual friction and entrainment are less visible than magnetic fields or bursts of radiation, but they are the quiet mechanisms that shape how the star breathes and turns. By binding the motion of neutrons, protons, and electrons together, they ensure stability while leaving signatures that careful observation can uncover. As timing data improve and gravitational wave astronomy matures, the ability to probe these mechanisms will only grow, tightening the link between microscopic interactions and macroscopic signals. At the extreme densities deeper in the neutron star core, theoretical models predict that additional baryonic species beyond neutrons and protons may appear. Among the most likely candidates are hyperons particles that contain strange quarks alongside the usual up and down quarks. The lightest hyperons include the lambda sigma and xi families, each with different quark combinations and charges. In ordinary matter on Earth, hyperons are unstable and decay quickly into protons and neutrons. Inside a neutron star core, however, the conditions are so dense that hyperons may become stable components of matter. The reasoning comes from chemical potential. As the density of neutrons rises, their Fermi energy becomes very large. At some point, it becomes energetically favorable for neutrons to transform into hyperons, even though hyperons are heavier. This transformation lowers the overall energy of the system, making hyperon formation possible. The densities at which hyperons appear are uncertain, but many models place the threshold at 2 to 3 times nuclear saturation density, which corresponds to the deepest regions of massive neutron stars. If hyperons appear in large numbers, they fundamentally change the composition of the core. They carry both baryon number and, in some cases, electric charge, altering the balance with electrons and muons. Their presence softens the equation of state, meaning that for a given pressure the density is higher. This has important consequences for neutron star structure. A softer equation of state reduces the maximum mass the star can support. Without hyperons, many models predict maximum masses well above 2 solar masses. With hyperons, the maximum mass can drop significantly, sometimes below observed values. This conflict is called the hyperon puzzle. Observations of heavy pulsars such as PSRJ 0740 plus 6620 with about 2 solar masses show that neutron stars must support at least that much weight. If hyperons appear too easily, stars would collapse to black holes before reaching such masses. Resolving the hyperon puzzle is one of the key challenges of dense matter physics. One proposed solution is that hyperon interactions are more repulsive at high density than simple models suggest. If hyperons repel each other strongly, they provide additional pressure that stiffens the equation of state and restores compatibility with observed masses. Another possibility is that hyperons are suppressed by phase transitions to other exotic states such as quark matter. In such scenarios, the threshold for hyperon formation is not reached before quarks deconfine. Experimental data to constrain hyperon interactions are scarce. Because hyperons are short-lived in laboratories, particle accelerators can produce them in high-energy collisions and hypernuclei, where hyperons are bound to ordinary nucleons have been studied. These experiments provide some information on hyperon-nucleon forces, but uncertainties remain large. Neutron stars are therefore the only natural laboratories where hyperons may exist stably in bulk. Observational signatures of hyperons are subtle. One potential effect is on cooling. Hyperons can open new direct Urca channels such as lambda, decaying into proton, electron, and antineutrino. These reactions are very efficient at neutrino emission and would cause rapid cooling. If hyperons are abundant, neutron stars would cool faster than observed. Thus, the relatively moderate cooling rates of many neutron stars suggest that either hyperons are absent rare, or their interactions suppress these processes. Another possible signature comes from tidal deformability, measured in gravitational wave events such as GW 170817. The deformability of a neutron star depends on the stiffness of its equation of state. If hyperons soften the equation of state significantly, tidal deformability would be lower. Observed values from gravitational wave mergers are consistent with moderately stiff equations of state placing constraints on the degree to which hyperons can soften matter. These observations do not rule out hyperons entirely, but suggest that if they appear, their effects must be tempered. Hyperons could also influence rotational dynamics. If present, they may form their own superfluid states, introducing additional vortex systems and complicating glitch behavior. Theoretical models of hyperon superfluidity suggest that lambda particles could pair in singlet channels, while sigma or xi hyperons may pair differently. The critical temperatures for such superfluids are uncertain, but if they exist, they would alter mutual friction and entrainment properties. Detecting such effects observationally is challenging, but future precision measurements may reveal discrepancies that point toward hyperons. The hyperon puzzle has driven much theoretical effort. Modern approaches use effective field theories, relativistic mean field models, and lattice quantum chromodynamics to estimate hyperon interactions. These calculations aim to reconcile the need for hyperons at high density with the observational requirement of heavy neutron stars. While progress has been made, uncertainties remain large, and consensus is not yet reached. Some researchers suggest that hyperons may appear only in the heaviest neutron stars near the maximum mass limit, while others propose that they appear earlier but are offset by strong repulsion. If hyperons exist in cores, they would represent the first stable bulk matter containing strange quarks in the universe. This would connect neutron stars to the broader field of strangeness physics studied in nuclear and particle experiments. Hyperons would also link astrophysics to heavy ion collisions where dense matter is briefly created. Even if hyperons are not abundant, studying their potential presence helps define the boundaries of the equation of state. By examining how models include or exclude them, physicists refine their understanding of strong interactions. The hyperon puzzle illustrates the feedback between theory and observation. Discoveries of massive pulsars forced theorists to reconsider hyperon models, while laboratory results on hypernuclei continue to provide partial guidance. Future measurements of neutron star masses, radii, and tidal deformabilities will sharpen constraints further. Gravitational wave astronomy in particular promises to improve knowledge of dense matter and help resolve whether hyperons truly occupy the inner cores of neutron stars. Until then, hyperons remain a leading candidate for exotic matter in dense interiors, a possibility grounded in basic physics but bounded by observation. Whether they are abundant or rare, their role in the story of neutron star cores cannot be ignored, and ongoing research continues to narrow the possibilities. At densities even higher than those where hyperons might appear, theoretical models suggest that mesons could condense into collective states inside neutron star cores. Mesons are particles made of a quark and an antiquark, and the lightest mesons are pions and kaons. In terrestrial environments, mesons are unstable and decay quickly, but in the extraordinary conditions of a neutron star core their behavior can be very different. The idea of meson condensation arises because at high densities, the chemical potential of electrons and the pressure of degenerate matter grow extremely large. It can become energetically favorable for electrons to be replaced by mesons, which then form a macroscopic condensate. This reduces the energy of the system while altering its composition and dynamics. Pion condensation was the earliest such possibility considered. Negative pions carry the same charge as electrons, and could substitute for them in maintaining charge neutrality. If the energy cost of creating pions falls below the electron chemical potential, pions may form and occupy a collective state. Instead of existing as individual particles, they would condense into a coherent field, somewhat like how photons form a laser beam, or how bosons form a Bose-Einstein condensate. In this state, they would participate collectively in interactions and significantly change the properties of the core. Later attention shifted to kaons, which are heavier mesons containing a strange quark. Negative kaons can also replace electrons, and under some models they condense more readily than pions, once strangeness degrees of freedom are included. Kaon condensation is favored in scenarios where interactions between kaons and nucleons lower the effective mass of kaons in dense matter. As density increases, this effective mass may fall enough that kaon condensation becomes the energetically preferred state. The appearance of a meson condensate softens the equation of state similar to hyperons. Because mesons carry charge, their condensation reduces the number of electrons and muons required for charge balance. This alters the composition and weakens the pressure support. As a result, the maximum mass of a neutron star with meson condensation is reduced. This prediction faces the same tension as the hyperon puzzle observations of two solar mass pulsars require equations of state stiff enough to support them. If meson condensates appear too easily, the maximum mass falls below observed values. Theories must therefore balance the possibility of meson condensation with the need to sustain high mass stars. One potential observational consequence of meson condensation is enhanced neutrino emission. In normal matter, the modified Urca process limits cooling rates. In the presence of meson condensates, new channels for neutrino production open up, especially through direct reactions involving mesons. For example, in a kaon condensate, nucleons can scatter and emit neutrinos through processes that are much more efficient than modified Urca. This would accelerate cooling dramatically. If many neutron stars showed extremely rapid cooling, it could point to meson condensation. However, most observed cooling curves are moderate, suggesting that if meson condensates exist, their role is limited, or their effects are balanced by other physics. Another possible signature of meson condensation lies in gravitational wave emission from neutron star mergers. During a merger, densities and temperatures rise, and if meson condensates are present, they may alter the stiffness of matter in ways detectable through the gravitational wave signal. The tidal deformability extracted from events like GW 170817 provides constraints on the equation of state. Too much softening from meson condensation would conflict with observed deformabilities. Thus, gravitational wave data indirectly limit the extent of meson condensation. Laboratory experiments cannot produce stable meson condensates, but heavy ion collisions provide partial analogies. Collisions at high energy briefly compress matter to several times nuclear density, creating conditions where pions and kaons are abundant. Measurements of kaon production in such experiments have been compared with theoretical models to infer how kaons behave in dense matter. Results suggest that kaon masses may decrease at high density, lending plausibility to the idea of kaon condensation, but uncertainties remain large. Theoretical treatments of meson condensation involve complex calculations using effective field theory and models of strong interactions. These must account for the interplay of nuclear forces, quark masses, and meson-nucleon couplings. Different models yield different thresholds for condensation, sometimes predicting onset at 2 to 3 times nuclear saturation density, and sometimes requiring much higher densities. This wide range reflects the lack of direct experimental constraints. If meson condensates do exist, they could form superfluid states with collective excitations. Such states would modify oscillation modes of the star, and could leave imprints in gravitational waves from oscillating or merging neutron stars. They might also interact with neutron and proton condensates, producing new coupling phenomena. For example, kaon condensates could coexist with hyperons or with deconfined quark matter, creating mixed phases with complex properties. One conceptual challenge is distinguishing whether hyperons meson condensates or quark matter appear first as density increases. All three possibilities soften the equation of state and compete with one another. Some models suggest a sequence where hyperons appear first, followed by kaon condensation, and then quark deconfinement. Others propose that one state dominates and suppresses the others. Determining the actual sequence requires both improved nuclear interaction models and more precise astrophysical data. Observationally, the discovery of massive neutron stars places strong limits on meson condensation. The existence of stars with masses around 2 solar masses rules out the simplest condensation models that predict early onset and large softening. However, more sophisticated models with repulsive interactions or mixed phases can accommodate both meson condensation and heavy stars. Gravitational wave astronomy promises to refine these constraints by measuring tidal deformabilities more precisely in future mergers. Neutrino observations from a nearby supernova would also test these ideas, since the cooling of the newborn neutron star depends sensitively on whether meson condensates accelerate energy loss. While the evidence for meson condensation remains indirect and uncertain, the concept illustrates how neutron star cores are natural laboratories for states of matter far beyond ordinary experience. Meson condensates would represent a form of macroscopic quantum matter built not from nucleons, but from bosonic particles carrying quark content. Their possible presence highlights the diversity of ways matter can organize itself when compressed beyond nuclear density. Whether or not they are realized in nature, meson condensates provide an important theoretical boundary case. Exploring their implications refines our understanding of strong interactions and guides the interpretation of astronomical data. By considering mesons alongside hyperons and quarks, physicists ensure that no plausible degree of freedom is overlooked in the quest to understand the deepest interiors of neutron stars. At the highest densities that may exist in neutron star cores, even hyperons and meson condensates may not remain the final form of matter. Many models predict that nucleons themselves dissolve into their constituent quarks, producing a state of deconfined quark matter. In this regime, the distinction between individual neutrons and protons disappears, and instead matter is described as a fluid of up, down, and possibly strange quarks. The concept of deconfined quark matter arises from the theory of quantum chromodynamics, which governs the strong force binding quarks into hadrons. At low densities, confinement keeps quarks locked inside nucleons, but at sufficiently high densities, the energy cost of confinement may become greater than allowing quarks to move freely. This transition is similar in spirit to how molecules in ice lose their ordered structure when ice melts into liquid water, though the underlying physics is much more complex. If quark matter appears, it may coexist with hadronic matter in a mixed phase, or replace it entirely in the inner core. The density threshold for deconfinement is uncertain. Some models place it at around 4 to 5 times nuclear saturation density, while others require higher values. Because only the most massive neutron stars reach such densities, not every star would contain quark matter. The possibility of quark matter is consistent with observed maximum masses near 2 solar masses, but the details depend on how stiff or soft the quark matter equation of state is. Quark matter can either soften or stiffen the equation of state depending on interactions. If interactions are weak, quark matter is relatively soft, lowering the maximum mass. If interactions are strong and repulsive, quark matter can provide additional pressure, allowing heavy stars to remain stable. This dual possibility makes observational constraints essential. One of the most intriguing possibilities in quark matter is color superconductivity. Quarks carry color charge, and like electrons in superconductors or neutrons in superfluids, they can form pairs. Because quarks come in 3 colors and several flavors, many pairing patterns are possible. At very high densities, the favored state is thought to be the color flavor-locked phase, in which up, down, and strange quarks pair in a highly symmetric pattern. In this state, quark matter is a color superconductor with an energy gap that suppresses scattering and alters transport. Other possible phases include 2-flavor superconductivity and crystalline color superconductivity, where pairing has spatial modulation. These exotic states have profound implications for transport cooling and stability. If quark matter exists in color superconducting phases, it will change neutrino emissivity. Pair breaking and formation processes in quark condensates can emit neutrinos, accelerating cooling. On the other hand, energy gaps suppress scattering, reducing some neutrino channels. The net effect depends on details of pairing. Observationally, if a star cooled more rapidly or more slowly than expected, quark matter could be a contributing factor. Gravitational waves from mergers provide another test. During the inspiral of 2 neutron stars, their tidal deformability depends on how stiff the inner core is. If quark matter is present and softens the core, the star deforms more easily. Measurements from GW 170817 suggest moderate deformability, consistent with some softening but not extreme. Future events with better precision could reveal whether quark matter contributes. After merger, the remnant may reach densities and temperatures that favor quark deconfinement, potentially producing signals in the post-merger gravitational wave spectrum. Detecting such signals would provide strong evidence for quark matter. Observations of massive pulsars also constrain quark matter. Any model with quark cores must still allow stars to reach at least 2 solar masses. Some models achieve this by invoking strong repulsion among quarks at high density. Lattice quantum chromodynamics. The numerical method used to simulate strong interactions is limited at high density because of computational challenges. Nevertheless, advances in effective theories provide guidance. These models are continually tested against neutron star observations, showing the close link between fundamental physics and astrophysics. Another possible observational consequence of quark matter is the presence of sharp phase transitions inside stars. If a neutron star with a hadronic envelope and quark core undergoes a sudden adjustment, it could produce observable signals. For instance, some theorists have suggested that glitches or flares could be connected to rearrangements at the quark-hadron boundary. Others proposed that sudden transitions during spin-down or accretion could lead to bursts of neutrinos or gravitational waves. While speculative, such scenarios demonstrate how sensitive neutron stars are to their interior composition. If quark matter forms, it may alter the relationship between mass and radius. Some models predict a separate branch of compact stars called hybrid stars, which contain quark cores but otherwise resemble neutron stars. In some cases, the mass-radius relation develops a twin branch where stars of the same mass but different radii exist, depending on whether they contain quark matter. Detecting such twins observationally would be strong evidence for phase transitions inside neutron stars. Current radius measurements from NICER suggest radii around 12 kilometers for stars near 2 solar masses, which do not strongly favor or rule out quark matter. More precise data may clarify the picture. Quark matter also raises questions about stability. Pure strange quark matter containing up-down and strange quarks in equal numbers has been proposed as an absolutely stable state, more stable than nuclear matter. If this hypothesis is true, then all neutron stars might ultimately convert into strange quark stars. However, current evidence does not support this scenario strongly, and the idea remains speculative. Still, it illustrates the profound implications of quark matter. Laboratory experiments provide limited direct information. Heavy ion collisions at facilities such as the relativistic Heavy Ion Collider and the Large Hadron Collider create quark-gluon plasma at high temperatures but low net densities. Neutron stars, by contrast, involve high density and low temperature. The two regimes complement each other but are not identical. Nevertheless, studying quark matter in the laboratory helps constrain theoretical models, which are then extrapolated to neutron star conditions. The coexistence of quark matter with superfluid neutrons and superconducting protons adds further complexity. Mixed phases with quark droplets embedded in hadronic matter could exist, altering conductivity and elasticity. Surface tension between phases may create structures analogous to nuclear pasta, but on a deeper level. These possibilities highlight how matter can organize itself in unexpected ways. The search for quark matter in neutron stars is ultimately a search for the limits of the strong force. Observations of masses, radii, tidal deformabilities, cooling rates, and rotational dynamics all feed into this effort. Each piece of data narrows the range of acceptable models. While no single observation has yet confirmed quark matter, the cumulative evidence points to the possibility that it exists in the most massive stars or in merger remnants. The study of quark matter bridges nuclear physics, astrophysics, and cosmology, showing how fundamental interactions govern the behavior of some of the most extreme objects in the universe. Whether neutron stars conceal deconfined quarks, color superconductors, or other exotic states, their interiors remain one of the greatest frontiers of modern physics, accessible only through the combined efforts of theory, experiment, and observation. The relationship between mass and radius is one of the most powerful tools for probing the physics of neutron star interiors. A neutron star is supported against gravity by the pressure of dense matter, and the equation of state determines how that pressure grows with density. Different equations of state produce different mass-radius curves. If matter is stiff, meaning pressure rises rapidly with density, the star can support more mass and has a larger radius. If matter is soft, the star is more compact and reaches collapse at lower mass. Measuring both mass and radius therefore provides direct constraints on the properties of dense matter. Observations of neutron star masses come primarily from binary systems, where the gravitational influence of a neutron star on its companion allows precise measurements. The discovery of pulsars with masses around two solar masses such as PSRJ, 1614-2230, and PSRJ 0740, plus 6,620 set firm lower bounds on the maximum mass. Any acceptable equation of state must support at least this much weight. This immediately rules out models that soften too quickly, such as some with unrestricted hyperon or meson condensation. The radius is harder to measure, but can be inferred from X-ray observations. When a neutron star emits thermal radiation from its surface, the observed spectrum depends on its radius as well as its distance and atmosphere. Instruments such as NICA on the International Space Station use precise timing of X-ray pulses to model the shape of the star as it bends light through gravity. By fitting pulse profiles, NICA has provided estimates of radii for several neutron stars with known masses. Results suggest that stars around two solar masses have radii near 12 kilometers, while lighter stars have similar or slightly smaller radii. These findings indicate that the equation of state is moderately stiff, neither extremely soft nor extremely rigid. Another observational channel is tidal deformability measured in gravitational wave events. When two neutron stars spiral toward each other, their gravitational fields distort each other. The degree of distortion or tidal deformability depends on how compressible the stars are. Soft equations of state lead to greater deformation, while stiff ones resist deformation. The first binary neutron star merger detected by LIGO and Virgo GW 170817 provided measurements of tidal deformability. The values inferred were consistent with radii around 11 to 13 kilometers, matching X-ray results. This convergence strengthens confidence in the constraints. Combining mass radius and tidal deformability data paints a coherent picture. The equation of state must be stiff enough to support two solar mass stars but soft enough to produce radii near 12 kilometers and tidal deformabilities within observed ranges. This rules out both extremely stiff models and extremely soft ones. It also places limits on the presence of exotic phases. If hyperons meson condensates or quark matter soften the equation of state too much, they conflict with observations. However, if these exotic phases are balanced by repulsive interactions or occur only at very high densities, they remain viable. The relationship between mass and radius is not only a constraint but also a way to search for phase transitions. If a sudden softening occurs at some density, the mass-radius curve can develop distinctive features. One possibility is a twin-star configuration, where two stars of the same mass have different radii depending on whether they contain exotic matter. Detecting such twins would be compelling evidence for phase transitions inside neutron stars. Current measurements are not precise enough to confirm or rule out twins, but future data from NICA and gravitational wave observatories may clarify the situation. Tidal deformability from mergers is particularly sensitive to phase transitions. If quark matter cores form during mergers, the post-merger gravitational wave spectrum may reveal characteristic frequencies. Detecting these signals requires more sensitive detectors, but planned upgrades to LIGO and Virgo, along with next-generation observatories such as the Einstein Telescope and Cosmic Explorer, aim to provide this capability. Mass radius constraints also connect to nuclear physics experiments. Properties of nuclear matter at lower densities such as symmetry energy and compressibility influence the extrapolation to higher densities. Measurements of neutron skin thickness in heavy nuclei studied through electron scattering experiments provide information about the symmetry energy. These results complement astrophysical data, tying laboratory physics to stellar interiors. Another connection is with heavy ion collisions which probe matter at several times nuclear density. While the temperatures are higher than in neutron stars, these experiments still test aspects of the nuclear equation of state. Comparing results from accelerators with astrophysical constraints helps refine models. The importance of precise measurements cannot be overstated. A difference of 1 kilometer in radius corresponds to significant differences in pressure at nuclear densities. Similarly, small changes in tidal deformability can shift the inferred equation of state dramatically. This is why NICE's ability to measure pulse profiles with millisecond accuracy and gravitational wave detectors' ability to extract tidal signatures are so valuable. Together they provide complementary constraints, reducing uncertainty and guiding theory. Observations also show diversity among neutron stars. Some appear hotter or cooler than expected, some glitch frequently, and some emit powerful bursts. These variations may reflect differences in interior composition and equation of state. By correlating mass radius measurements with other behaviors, researchers hope to uncover deeper links between microphysics and macroscopic phenomena. For example, stars near the maximum mass may behave differently during glitches or cooling because their cores are denser and possibly contain exotic matter. Modeling these connections requires accurate equations of state, consistent with observational bounds. Another aspect of mass radius constraints is their role in merger astrophysics. The outcome of a binary neutron star merger depends on the maximum mass. If the combined mass exceeds this limit, the remnant collapses quickly to a black hole. If it does not, the remnant may survive temporarily as a hypermassive or supramassive neutron star supported by differential rotation or thermal pressure. Observed electromagnetic counterparts such as kilonova light curves depend on how long the remnant lives. Thus, mass radius constraints feed directly into models of merger outcomes and multi-messenger astronomy. The study of neutron stars is therefore a synthesis of observation and theory. Mass and radius measurements connect gravitational physics, nuclear interactions, and astrophysical modeling. Each new pulsar mass measurement or NICE radius estimate sharpens the allowed range for the equation of state. Each new merger detected by gravitational wave observatories adds data on tidal deformability. Together these pieces reduce uncertainty and reveal how matter behaves at densities impossible to achieve in laboratories. The emerging picture is of an equation of state that is neither too soft nor too stiff, consistent with stars of around 12 kilometer radius and maximum masses above 2 solar masses. Within this framework, exotic matter may still exist, but only if its effects are moderated. As more data arrive, the allowed window will narrow further, eventually distinguishing between competing models of hyperons, meson condensates, and quark matter. Despite decades of progress, many aspects of neutron star cores remain uncertain, and the frontier of research continues to move as new data arrive. Observations with X-ray telescopes, gravitational wave detectors, and radio timing arrays each provide partial views of the interior, but the complete picture is still incomplete. One major uncertainty is the exact equation of state of dense matter. Models differ in how pressure grows with density. and while broad constraints from mass radius and tidal deformability are now established, the fine details remain debated. These details determine whether hyperons appear, whether meson condensation occurs, and whether quark matter cores are common. Even within nucleonic models, uncertainties in the nuclear symmetry energy and three body forces among nucleons create variations that alter predictions. Laboratory experiments help reduce these uncertainties but cannot reach the densities of neutron star cores, leaving astrophysical observations as the primary guide. Another uncertainty concerns the critical temperatures for superfluid and superconducting phases. While evidence supports their existence, the exact density dependence of pairing gaps is not well known. This uncertainty affects predictions of cooling behavior, glitch recovery timescales, and neutrino emission. Observations such as the rapid cooling of the neutron star in Cassiopeia provide important clues, but they are still open to interpretation. Improving theoretical models of pairing, particularly for triplet-state neutron pairing, at high density remains a priority. The behavior of magnetic fields inside neutron stars is also unresolved. While superconductivity implies flux tube lattices, the details of flux tube motion pinning and interaction with vortices are not well constrained. These processes influence both long-term magnetic field decay and sudden events such as magnetar flares. Simulations have advanced, but the range of scales from microscopic quantum interactions to global magnetic geometry makes the problem formidable. Direct observational signatures of flux tube dynamics are elusive, leaving many open questions. Gravitational waves offer a new window on neutron star interiors, but current sensitivity is limited. The in-spiral phase of binary mergers has already constrained tidal deformability, but post-merger signals which could reveal phase transitions or the presence of quark matter remain out of reach. Next-generation observatories such as the Einstein Telescope and Cosmic Explorer aim to detect these signals. If successful, they may provide direct evidence of exotic matter. Continuous gravitational waves from oscillating or rotating neutron stars could also reveal information about internal structure, but so far no such signals have been detected. Another uncertainty is the composition of the deepest core. Hyperons, meson condensates, and deconfined quarks are all possible, but their relative roles are unclear. The hyperon puzzle in particular remains unresolved. If hyperons appear, they must be strongly repulsive to avoid softening the equation of state too much. If they are absent, some other mechanism must relieve the high neutron Fermi energy. Meson condensates face similar constraints, and quark matter models depend on poorly known strong interaction physics at high density. Distinguishing among these possibilities will require more precise mass radius measurements, better tidal deformability constraints, and eventually gravitational wave signals from post-merger remnants. Thermal evolution also contains uncertainties. While cooling curves provide information about neutrino processes, variations among stars are large. Some stars cool quickly, while others remain relatively warm for their age. These differences may reflect variations in mass composition and magnetic field, but disentangling the effect is challenging. Accreting neutron stars provide additional data, but interpreting crustal cooling requires detailed modeling of nuclear reactions in the crust which themselves are uncertain. Future X-ray missions with higher sensitivity may help resolve these puzzles. The role of rotation continues to present open questions. While glitches are well explained by vortex unpinning details of vortex pinning, strength creep and interaction with flux tubes are not fully understood. Timing data reveal a variety of glitch behaviors across different pulses, and no single model explains all cases. The stability of R modes also remains uncertain. Whether mutual friction and viscosity are strong enough to suppress gravitational wave emission is still debated. Detecting or ruling out R modes observationally would clarify this issue, but current data are inconclusive. Advances in nuclear physics are closely tied to these astrophysical uncertainties. Experiments on neutron-rich isotopes, such as those at rare isotope facilities, provide input on nuclear forces that can be extrapolated to neutron star densities. Measurements of neutron skin thickness in heavy nuclei connect to the symmetry energy, which influences the proton fraction in neutron star matter. These laboratory results complement astrophysical observations, providing a cross-disciplinary approach to the problem. Another open area is the interaction of neutron stars with their environment. Accretion from a companion star alters the crust and influences cooling. Magnetic field burial and re-emergence during accretion depend on conductivity and superconductivity in the core. Understanding these processes is essential for interpreting observations of X-ray binaries and millisecond pulsars. Similarly, magnetobursts and flares require models that connect crust fractures, magnetic reconnection, and core processes. Each event observed provides partial evidence, but comprehensive models remain a work in progress. Looking ahead, future observatories promise major advances. NASA continues to refine mass and radius measurements, and proposed missions such as Athena and Lynx could provide even better X-ray spectroscopy. Gravitational wave detectors will improve sensitivity, enabling measurements of post-merger signals and continuous waves. Neutrino detectors may one day capture neutrinos from a nearby supernova, providing direct evidence of the birth and early cooling of a neutron star. Combined, these observations will reduce uncertainties and test theoretical predictions. The strange physics inside neutron star cores will become clearer step by step, though likely never entirely settled as new discoveries bring new questions. In the meantime, models must remain flexible, incorporating both nucleonic matter and the possibility of exotic phases. The convergence of multiple lines of evidence is essential. Mass measurements set firm lower limits, radius and tidal deformability, constrain stiffness, cooling curves reveal neutrino processes, glitches probe superfluid dynamics, magnetar activity tests, crust and field interactions and gravitational waves promise to reveal phase transitions. Each dataset is incomplete alone, but together they triangulate the truth. Neutron star interiors remain beyond direct experimentation, but they are not beyond scientific reach. Through the patient combination of astrophysical observation, nuclear physics experiments, and theoretical modeling, the uncertainties are narrowing. The challenge is to interpret all signals consistently, without over-reliance on any single model. In this way, the field continues to progress, with each new discovery refining the picture of how matter behaves at extremes of density pressure and magnetic field strength. Neutron stars thus remain both enigmatic and revealing, showing the limits of current understanding, while pointing the way toward deeper truths about the fundamental forces of nature.